All right, folks. Well, wanted to give a little bit of an intro to classes and objects. This is something we'll spend a lot of time on in future courses, but just to give you a bit of a feel for it, and if this is the only programming class that you take, then this will give you a good lead in if you want to move into any of the OO languages like Java or JavaScript, or most languages now provide some form of OO support. So we looked at structs as a way to take a bunch of different data fields and group them together into kind of a single logical unit. Well, with abstract data types, we discussed the idea of also lumping in the operations on those data types. So if you had a point and you wanted a function to print a point, you could somehow lump those things together. So you'd have maybe your point coordinates and this function to print the point coordinates all lumped into this one point item. Well, classes are going to give us a way of doing that. Right? Structs in a conventional sense, and technically you can do it in C++, but in the conventional usage, structs don't give us that capability. So we'll introduce classes that allow us to do that. They also provide a lot of additional functionality and a lot of additional design potential, and we'll talk about ideas of building data types based on construction of other data types, so concepts like inheritance, but we'll get into that in a few minutes. So a class in C++ uses syntax that's a lot like the syntax we used for structs. So it's going to look pretty similar, but again, we'll now be able to define functions inside this class, inside the collection of data fields, if you like. Now, just in terms of naming terminology, when we have a standalone function, we refer to it as exactly that, a function. When one is part of a class, we refer to it as a method. So a lot of the same ideas, it's just that when a function is defined as a part of a class, we'll call it a method, and it actually has access to all of the data fields that are stored inside the class. So we'll get into this a little bit as we go along. Now, when we create, so our class is the data type, right? Just like with our structs, the struct was the data type, and we could create variables of that type. So it'll be the same idea with classes. The class describes a kind of data, a kind of item, and then we'll create variables that are of that data type. So if we had a class representing a point, then we could create variables that were points, if you like, and they'd each have the methods and the fields associated with that class. As far as terminology goes, those variables are typically referred to as objects or as instances of the class. So if you hear either of those terms crop up, that's all that we're saying, is that we've got the class data type. Here we're actually creating an item of that type, an object of that type, or an instance of that type. Now, I mentioned classes give us more features beyond just the ability to include methods as a part of the class. We can also classify each of the fields and each of the methods as either public or private. There's actually also a protected later, but we'll get into that. So public means that anybody can get at that field through your variable, through the instance of the class, through an object. So I can say something like x dot whatever the field is and use that to access it. So if it's public, we can get at it from anywhere in the code as long as we've got a class variable to play with. If it's private, that means that only the class methods can access them. So the main routine, for instance, couldn't refer to x dot some method if it was private, or x dot some field if it was private. Only the actual class methods can get at them. And so we'll have a bit of a play with that as we get deeper into the class examples here. So the syntax. I mentioned it looks a lot like the struct syntax. So again, it's class instead of struct, whatever we want to give as a name for our new type, and the open and close curly brackets and a semicolon to end it, and a bunch of data fields inside. So that part looks just like with our structs. But now we can actually give the prototypes for different methods inside. So in this case, let's say we want a class to represent an array of floats that we're going to dynamically allocate. So we'll have the pointer that we'll use to keep track of wherever this array gets allocated. So let's say it's an array of floats, so a float star and the name of our array. And then we'll want to keep track of how big an array we allocated and how much of that we're actually using so far. So maybe we're only using the first 10 spaces, but we allocated 100. So we'll have a float pointer for the array itself, and a couple of ints for the size allocated and the size that we're currently using. So that part, again, is a lot like structs. We're going to make this private, though, so from outside, from things like the main routine, for instance, you couldn't say, array.i or array.allocated or array.inUse because it wouldn't have access to that private content. Then we create the prototypes for all these different methods. So allocate will actually create the array. We tell it what size, it'll create the array, and initialize allocated and in use. We might have a set function where we say, here's a position and here's a value, put it in the array at that position. Lookup, here's a position, look up what value is stored there. And maybe each of these is going to return a Boolean where it's true if it worked and false if something went wrong. Right? Because there are possibilities for things that go wrong. Right? Somebody gives us a position that's out of bounds and negative or too big, or somebody gives us a size that is invalid, or we can't actually allocate that much space. So each of these can return a true false based on whether it worked or not. So again, just an example of the syntax for setting up the prototypes for the methods and the data fields that we want to use, and deciding which things we want other parts of the program to be able to use and which things only the methods themselves can access. So somewhere we've got to give the actual implementation of those methods, right? We gave the prototypes. Now, when we do that, right, we've got something, let's look at our set for a moment. So we've got a function to set the value in our array. Well, if I've got a whole bunch of different classes defined, there might be a whole bunch of them that each have some kind of a set function, right, to set some value someplace. Or maybe I've got a print function to print the contents of the array. Well, there might be lots of different classes that have print functions, or print methods rather. So when I go to implement it, right, in say a .cpp file to go along with my class, then I have to give the name of the method, but I also have to say which class this is for. So for instance, if I had a print method, I'd say the name of the class and then the name of the method. So here, just as an example for our allocate, right, we had our function that had a return type of bool, the name was allocate, it had a size parameter, and so when we give the implementation for it, we say, okay, this is part of the float array class, then you give the 2 colons, and again, that's just the syntax rules for identifying the class name, 2 colons, method name. And then inside, you give the implementation of your method. Now, in here, we can actually use any of the fields from the class. So we can use R, and we can use allocated, and we can use in use just directly inside the method. Again, the method's part of the class, so it's got direct access to those fields. So we can make use of R, we can make use of size, we can make use of allocated. And again, this is pretty much just the code for our typical dynamic allocation of an array. Right, we'll go through, initialize some values in case things don't go right. As long as the size is positive, we'll try and allocate a new array, check whether that worked or not. If it worked, then we'll set the appropriate size and return true. Right, and if it didn't work, we'll return false. Now, in the main routine, again, you'd go through the same sort of process for the other methods for the class. In the main routine, we want to be able to use this class. So I want to be able to create an array and use the methods. So float array is the name of my class, so I can create a variable that's one of these things, that's an array of floats. So I'm going to call it my array. So this just goes through and creates my array of floats. We haven't talked about how to set default values for these things. We'll get into that in a little bit, but this goes off and creates one, does some initialization for it. And then I want to try calling one of those methods. I want to try and call allocate. And so I'll say, I want to create an array of 10 floats. So I call allocate size 10, and I'm calling it through my array. So my array is going to have, well, it's going to go through this allocation process and set its allocate and size and in-use fields. And again, this is going to return a true or a false. So if it succeeds, then I'll go ahead and do things with it. And then somewhere in here, I'd also wind up deallocating it, but we'll worry about that at another point. But again, I can go through and I can call methods through my object, through my instance of that class, through my variable. So my array is the array, or my array class, my float array class. So I can, anytime I want, I can say, okay, for this item, call the set method and pass these parameters. For this item, call the allocate method and pass these parameters. And again, in terms of the public and the private, the main routine can access things that are public, but can't access things that are private. So suppose we have some class where we've got an integer field named data and a void method named foo. If I do my calls to foo, that works as long as foo is public. Or if I try and access the data field, that works as long as it's public. It fails if either of those are private. Right? If foo was in the private section, then the main routine couldn't access it. If data was in the private section, then the main routine couldn't access it, even though it's got the variable. Right? That portion of the class is locked off from outside use. Now, I mentioned that there was this idea that somehow we had to initialize these things. So there are a couple of special methods associated with each class. So a constructor is one that essentially goes through and initializes the values in a particular object. And a destructor is one that goes through and cleans things up later. So in the example where our float array used dynamic allocation, right? It allocated this array of space. When we finally got rid of the object, we'd want to do a delete on that space to deallocate it. So a destructor would be a function that's automatically called when at the end of the lifetime of a particular variable, and it takes care of any cleanup that has to happen. So constructors are used for initialization, destructors are used for cleanup, and they each have a special name. So the constructor has the exact same name as the class, and we'll show what that looks like in just a second. And the destructor has the same name as the class, except it's got a tilde in front to distinguish it from the constructor. And what's a little unusual is that these have no return type. So if I create a class that's going to represent a point, so let's say we've got the x and y coordinates are private data fields, and we'll have a constructor, so it's named point, and a destructor that's named tilde point. And again, they have no return type. So that's going to be, the constructor is going to be to initialize our point, the destructor is going to be to clean it up at the end. Destructor is not going to have anything much to do in this particular case, but we'll have one. Let's have a set method to go through and set a new x and y value, and a print method just to display them. So again, my constructor might stick in default values, or it might ask the user to provide values. So in this case, let's do that. Let's prompt the user to enter values for x and y, and we'll read them in. And again, it can access the private fields because point is part of the class. Our point constructor is part of the class. So we just read it into x and y. Our destructor, again, there's nothing that particularly has to be cleaned up in a case like this. So just for example, we'll just have it print out, this is the end of, and we'll print the point coordinates. Our set method, we want to be able to pass an x value and a y value and actually store those in x and y inside the object. So we'll just set x to the x value and y to the y value. And our print, again, is just going to print the current x and y values. But again, we can show a constructor and show a destructor. And where they run is at the point where the point is, at the spot where the point is first created, that's when the constructor runs. So right at this spot in the program execution, our constructor is going to run. And as soon as the main routine ends and effectively the point ceases to exist, that's when the destructor will run. So constructor when the thing is created, destructor when it ceases to exist. If I had a main routine and all it did was to declare those 3 points, A, B, and C, if I was to run that, the constructor for each of them would run, and then the destructor for each of them would run. So you can have functions that run even though you never see an explicit call to them. right? Just because it's the constructor and destructor that are going through and doing this. So I mentioned the idea of more special features, building classes off of other classes. So I'm just going to introduce the concept of inheritance. And again, we'll play with this a lot more next semester. But you can base a new class on the content of an old class. So you can say, I want to create this new class, and I want it to use everything from this other existing class, and then I'm going to add some more stuff. So you can inherit fields and methods from some other existing class, and then add your own, or even replace some of the existing ones. So let's say I've got a circle class, and it's got coordinates for the center of the circle, and it's got a radius. So it's got these 3 data fields. It's got a constructor and a destructor, something to print it, something to set the XY coordinates if we want to change them, something to set the radius if we want to change that. Somewhere we've got the methods actually implemented for this. And then I decide I want a sphere class that's going to be 3-dimensional instead of 2-dimensional. So I want to inherit all of this stuff from the circle, but then add some new things. So I'm going to inherit, and you can inherit publicly or privately as a way of kind of restricting access to the fields and methods that you're inheriting. But we'll leave that discussion for another day. So we'll inherit from the circle class. So sphere automatically gets an X and a Y field. It automatically gets a radius field. It automatically gets the circle constructors and destructors, and the print and the set point and the set radius methods. We'll add a Z field, right, for a Z coordinate. We'll add constructors and destructors for sphere, and we'll add a method to set the value of Z, and a method to print, let's say, all 3 of the coordinates, X, Y, and Z. And so the set Z is brand new, so it's just added. The print overrides, if we just say, if we create a sphere and we call print, it's going to use the sphere version instead of the circle version. There are ways we can still get at the circle version, but again, I'll leave that for a discussion for another day. But we can go through and add new fields, add new methods, and we can override existing fields or existing methods. Now, one of the interesting things about this is it allows us to create these hierarchies of classes where they're inheriting from one another, and they're getting more and more specialized as we go down. So we could come up with, let's say we want to represent in our program all sorts of different vehicles. So I might create a base class called vehicle that just has the fields and the methods that every single kind of vehicle is going to need. I don't know, maybe it's got the name of the vehicle and it's got the vehicle mass, the weight, or something like that. But then we can create specializations. We could create air vehicles, land vehicles, sea vehicles. So for each of these we could create a class, and that would have the fields and methods shared by all land vehicles, the fields and methods shared by all sea vehicles, the fields and methods shared by all air vehicles. And then again, we could specialize on those. For land vehicles, we could have 2-wheel versus 4-wheel. For sea, we could have boats versus subs. For air, we could have, gliders versus props versus jets. All right, so we can specialize. And when I want to make a change to a class, I change the appropriate level of detail. So if I want to make a change that affects all vehicles, I make that in the vehicle class. If I want to make a change that affects all land vehicles, I make it in the land class. If I want to make a change that affects just 4-wheel vehicles, I make it in the 4-wheel class. So this allows us to target our fields and our methods at how broadly they apply. And again, each of these classes inherits the fields and the methods from their parent, and from their parent, and from their parent, and so on up the chain. So it does give us a very powerful way of customizing our designs and of creating a design where we have minimal repetition of code, right? Instead of having some method that I put in vehicle, or instead of having some one method that's the same in glider and prop and jet and 2-wheel and 4-wheel and boat and sub, I put that in vehicle, so it only appears in the one spot. And if I want to modify it, I only have to modify it in the one spot. So this is a very powerful design tool. All right, I want to just quickly run through one example playing with this stuff. We won't spend too much time on it, but just to kind of see it in action. So I've got a critter class. And what I'm going to do is I'm going to break my code up into three different files in this case. So I'm going to put the definition of my critter class in what's called a header file. And so we'll take a look at the contents of that in just a second. I'm going to put the implementation of the prototypes in a .cpp file that's just got code implementations for critter. And then I'm going to put the program that uses my critter in yet another .cpp file. And this is going to allow me to start breaking my code up into files. And when I'm writing programs in the future, I can write my programs to use the appropriate other pieces of code that I've already written. So if I want to create 5 different programs that all use critters, I can create these different programs in their own .cpp files, but each of them is going to make use of the code that comes from critter.cpp and critter.h. So let's just take a look at the critter.h for a moment to show what that looks like. So here I'm going to have, when we create header files, there are some issues in including them. The pragma once is just meant to deal with that. I'll save that discussion for yet another day too. So I'm going to include any libraries that I want, specify the namespace that I want, and then I'm going to give the definition for my critter class. So I'm going to say critters have a name and a breed that are just going to be strings and an age that's just going to be an integer. And I'm going to provide a few methods for my critter class. Right? I can print a critter. I can look up the name, breed, and age for a critter, and so I'll just stuff those into pass-by-reference parameters. And I can allow the user to set a new name, breed, and age. So I'm going to have these 3 methods, and then the constructor to initialize a critter, and the destructor to clean it up. Destructor's not going to have to do much, but we'll show it again for completeness. So there's my class definition in this header file. So in my critter.cpp file, I'll provide the implementations of those critter methods. So what I'm going to do is include that critter.h, which basically says use the definitions from critter.h. It acts kind of like cutting and pasting it here. And I'm going to provide implementations for those methods. Right? So for my critter class, for the print method, I'm going to go through and it's just going to print out the name and the breed and the age. For my critter class, for the lookup method, right, I want to copy name into one parameter, breed into another, and age into another. So it's just going to do that. For my set from user, I'm going to prompt the user to enter a new name, breed, and age, and I'll just read those in. Again, we should throw in error checking, but you know how to do that at this point. My constructor is just going to initialize them, so we're just going to initialize name to an empty string, breed to an empty string, and age to 0. And I'm going to print out setting up the critter here just so you can see when this constructor actually runs. And for my destructor, well, it doesn't really have to do anything. There was no dynamic allocation in this example. But I'm going to throw in a cout statement just so you can see where this runs. So we'll print out cleaning up the critter. Now, I want a program that's going to use critters. So this is going to be in my crit.expt.cpp. And so for this one, I'm going to say, okay, I want to use the critter that was defined in critter.h, so I hash include it. And you'll note that when I'm including my own code, I use the double quotes instead of those angle brackets. The angle brackets were for the built-in libraries, and these double quotes are for header files that I've created, definitions that I've created. So the main routine can go through and use critter the way it was defined in that critter.h file. So I can create variables of type critter. I can create so I'll call this one crit. And what we'll do is, first off, we'll call the print method just to show that the default values actually got set for our critter. And then we'll call set from user and get them to enter a name, a breed, and an age for it. And we'll print that out to make sure it worked. And then we'll try that lookup function. So I'll have strings for name, breed, and age, and I'll just look up those values from the critter and print those out just to show that that worked. And again, hopefully at the beginning, where crit is declared, we should see the constructor run. And at the end, when crit ceases to exist, we should see the destructor run. So we'll just see if that works out. Now, I've got these 3 separate files that are all involved. the two .cpp files each included that .h, so they've each got access to the .h content. But if I want to create a program, I have to compile these two CPP files together. So I'm going to compile, I'm going to use my warning flags here. I'm going to compile critter.cpp together with the crit expt.cpp, and I'm going to create an executable, let's say called critx. And hopefully it compiles. Yay! And so we'll try running it. So we'll try running our crit expt. And so we see that setting up the critter, right? That came from when the constructor ran. And then the printing out whatever those default values were. So it's got an empty string for the name, an empty string for the breed, and then the 0 for the age. And now the set from user method is asking us to enter a name for our critter, and a breed, and an age, and it should print that out. Yay! And then we tried that lookup function to go get those values, and it looked up those successfully. And then we saw the message from the destructor when it ran at the very end. So again, you can see how this stuff works. All right, I just wanted to run through that as a bit of an example on how we can start creating these things, how we can start using these things. And again, it's something we'll spend a lot of time on next semester and in future courses. All right, I will leave that there.